Well, just like with the derivative review, I'm going to start by giving the 5 main derivative relationships that we're going to see in this class, and you'll see why as I go into this. So remember, we know that I'm going to leave out the function symbols and stuff to sort of simplify the look of this, but remember that the velocity, although even though I didn't write it in here, we're talking about velocity as a function of time, a velocity that's represented at any time you choose. Velocity is the derivative of the position with respect to time. Second, the acceleration is the derivative of the velocity with respect to time. Third, the angular velocity of a rigid body is the derivative of the angular position with respect to time. Fourth, the angular acceleration is equal to the derivative of the angular velocity with respect to time. And last, the only one that is not a derivative with respect to time, we know that the force applied to an object is the negative derivative of the potential energy with respect to x. Okay, so, and remember that you want to keep these in mind all the time in this class. Okay, well, we talked last time about, so let's look at this first one, the one we'll see the most of these 5. If you're given the position as a function of time, say that you know that at any time the position is equal to the time squared, okay, then it's easy to take the derivative to figure out what the velocity is at any time, okay? But what if you're not given the position as a function of time? What if instead you're given the velocity as a function of time? How hard is it to figure out the position? In other words, to work in the opposite direction. You're given the thing on the left and you want to find the function on the right. How hard is that to do? Well, the first fundamental theorem of calculus says that the opposite of the derivative is the integral. And so you can think of it this way. That is not how you spell it. Integral. Okay. So the integral, it is the function whose derivative is the given function. Okay, so in all of these cases, all of these 5 cases, if you were given the thing on the left and you wanted to calculate the function on the right, you could do that by starting with the function on the left and then taking the integral with respect to that variable. So for example, if you know the velocity as a function of time, you can take the integral of that function with respect to time and it'll give you the position. Okay, so some things to remember about integrals. I did this when I was talking about derivatives too. There's one additional one here that is an important one. But first, okay, integrals only work with functions, just like with derivatives. So these only work for functions, not just single values of a variable, like say at a single instant. Second, you always have to take an integral with respect to a variable, just like a derivative. So you need to take the integral with respect to a specific variable, and again, that's just like a derivative. And now the last one, this is the one we didn't see with the derivative, and that is every time you take an integral, there's a constant of integration. So there's always a constant of integration. And this is no small thing. This is something that we're going to have to deal with of integration. We're going to have to deal with this all the time. So first I want to explain why this is. So like where does the constant of integration come from? Okay. Well, think of the function f of x is equal to 2. Okay, I'm just making up this one simple function. And what we're looking for is we want a new function. I'll call it capital F of x. That has a slope everywhere of 2. Since this is such a simple function, you know, f of x equals 2 is pretty close to as simple as it gets. It's not too hard to come up with a solution to this. So if we're plotting our function capital F versus x, what's a function capital F of x that has a slope of 2 everywhere? Well, here's one. So this is the function capital F of x is equal to 2x. Okay. Is that the only function, though, that has a slope of 2 everywhere? Well, no, because the slope doesn't care about the position of this thing. So here's another one that works. I'm trying to make these parallel. Here's another one, another one. There's infinitely many of these. And they're all parallel to that first black line that I drew. But you can move them up or down. And moving this function up or down has the effect of adding some unknown value that can be anything to our function capital F is equal to 2x. And that's the constant of integration. So that's the unknown c. And whatever c you choose determines which of these infinitely many red diagonal lines you get. Okay, so that's where the constant of integration comes from. When you talked about this in math, you probably, you were asked to include that in your answers. And it was sort of an abstract thing. In physics, we're going to see that in every case, that C really represents something that's physically important. The type of integrals that we're going to have to do, just like with derivatives, we had simple functions. With integrals, we're also going to only do sort of the simplest functions. So here are the functions you'll need to calculate integrals for. When we did derivatives, there were 3 of them. There were polynomials, natural logarithms, and trig functions. In this case, it's really only 2 of them. The first one is polynomials. And you'll see why there's only 2 when there were 3 with derivatives before. The first type of polynomial is, so if you're taking the integral of a function that is c times x to the r with respect to x, you're sort of doing a derivative in reverse. And so the answer to this is going to be c times x to the r plus 1 divided by r plus 1. And then you'll have to add on a constant of integration. I've already used this c, so this time I'm going to call my constant of integration k. That's just some unknown thing you're adding to it. But the key thing here is that this, I mean, it works for almost everything, but this doesn't work for r equal to -1. You're going to have to do something else when r is equal to -1. Okay, well, the second one is, what do you do if r is equal to -1? So the integral of c x to the -1 dx. And maybe you notice that x to the -1 is 1 over x. And if you think back to what I was saying about derivatives, the derivative of natural log is equal to 1 over x. So maybe you'd expect some kind of natural log thing to come up, and that's exactly how it works. So this is equal to that c times the natural log of x, and then you have to add on the constant of integration. Okay, so you have one case for any r value that's not equal to -1, and then a different way of doing it when the r value is -1. And then the second one is the trig functions. That's just like before. So the first one is if you're taking the integral of c times the sine of x with respect to x. This is equal to, I think I did it actually in the other order before, so let me keep it in the same order that I did in the derivative one. So if you have a constant c times the cosine of x integrated with respect to x, your answer is going to be c times the sine of x plus this constant of integration. And then if you're taking the integral of c times the sine of x with respect to x, what you get is -c times the cosine of x plus the constant of integration. And in all of these cases, what you would see is if you did the integral and then went right back and took the derivative, you'd get your original function back. Integrals and derivatives just undo each other. Okay, well, let's do an example problem. Okay, so let's say that in this case, I'm going to go back to these 5 derivative relationships. And let's say that in this case, we are given, let's say, the angular velocity as a function of time, and we want to figure out the angular position as a function of time. So we'll say that the angular velocity is a function of time, is equal to, let's say, 5t squared minus 4t to the minus 1 plus 2 cosine of t. And we want to calculate the angular position of this rigid body as a function of time. Well, we're just going to go term by term. And so the angular position as a function of time is equal to 5t to the third over 3 minus 4 times the natural log of time plus 2 times the sine of t. And then don't forget your constant of integration. I'll go back to calling this c because we didn't have a c in it already. Okay, so just using those rules, you can go in the opposite direction of the derivatives for these relationships. Okay, well, what do you do with these constants of integration? We're not going to want to keep these in your math classes. You probably just kept them as a constant and sort of that was the end of it. But what we want to do is calculate what that constant is. So how do we determine what the constant of integration is? The way that we are going to do it is with initial conditions. And so we're going to always be given the value of the function we're trying to calculate when time is equal to 0. Okay, so let me just, instead of trying to describe this, I'm just going to do it as an example. So let's say that we're given that the velocity of a particle as a function of time is equal to t squared. And we want to know what's the position as a function of time given that when time is equal to 0, p is equal to minus 2. Okay? Well, to find position as a function of time, we have to integrate this velocity as a function of time. And so the position is equal to the integral of t squared with respect to time. And so p is equal to t cubed over 3 plus this constant of integration. Now we can calculate this constant of integration by using this information. So what we're going to do is we're going to plug in 0 for t and negative 2 for p, and we're going to calculate this c. Okay? So we're going to say, I'm going to write it as the position when time is equal to 2 is equal to negative 2. That's what we're given. And it's equal to 0 cubed over 3 plus c. Okay, well, negative 2 then is equal to 0 plus c. So c is equal to negative 2. And therefore, the final function representing the position is, we already knew it was this. Okay, we just didn't know what c was yet. Now we've calculated that, and this is equal to t cubed over 3 minus 2. Okay, so with the derivative and the integral, now we know how to go in both directions from one function to another with these 5 key derivative relationships for the class.